Previously, we established the integration by parts formula, which is used for certain antiderivatives where a basic U substitution won't work, right? And that this technique is based on reversing the product rule. Now, there are some instances where the integration by parts process has to be applied more than once, right? So, we might refer to that as repeated integration by parts. Now, what does it look like? Well, let's start with an example. So let's say we have the integral of x squared times the sine of x, right? Now, when we look at it, we realize, yep, there is really no composite here. That will help. And we can identify our two types of functions, so the x squared, that would be an algebraic, so an A type. And then, of course, the sine function is trigonometric, so that would be a T type. And based on Lie-8, what we would say is we would choose, since the A comes first in Lie-8, we're going to choose our U to be x squared, and then everything else by default will be our dv, right? So let's do that. So let U equals x squared, and then dv is equal to the sine of x dx. So just as a reminder, here is our basic formula for the integration by parts. So the integral of u dv is equal to uv minus the integral of v du. So we have a couple pieces that we need for this formula, but we need to find a few more, right? So first we need to differentiate our u. So our differential du is 2x dx. And v, which would be the antiderivative of our sine function, is going to be negative cosine of x. All right? So pretty straightforward so far. So let's write down what we have. So our original integral, the integral of x squared sine of x dx, is equal to u times v. So that's going to be x squared times negative cosine of x. So I'll write that as negative x squared cosine of x, and then minus the integral of v du. Well, here's our v. It's negative cosine of x, and then it's times our du, which is 2x dx. Now, what we can do, certainly, we can see we have this double negative here. We have a constant here that we can pull out. So let's simplify this part of it just a little bit more and then look closely at what we've done. So taking out that negative makes it a positive in front of the antiderivative sign, and then also we can take out the 2, so we will end up with a plus 2, and then inside we still have an x. So again, I like to put the polynomials in front of the trigonometric function, so x cosine of x dx, right? So we've made progress, right? We've made progress. We started with an x squared times or sine function, and we've used the integration by parts process, and we've broken it down to a slightly easier integral. Easier in the sense that, okay, on this side we have x squared multiplying a trig function, and then over here we have x multiplying a trig function. So it's still not at a point where we can write down what the antiderivative is. So integration by parts needs to be applied again. And what's interesting is we still have an A type, so this is our algebraic function, and this is our trigonometric function, right? Our T type. Well, let's, again, based on that, choose another pair of U and dV. So again, U is going to be our algebraic function. In this case, it's x. And then obviously whatever remains, that's going to be our dv. So dv is going to be equal to the cosine of x dx. Again, let's compute du. Now, the benefit of doing parts again is that when I differentiate x, it just becomes a 1. So du is equal to dx, and then our v, antiderivative of cosine, is sine, right? Now, what we're doing here, this second iteration of the integration by parts process, is to simplify this particular integral. So when I apply parts again, this is going to be replaced with the uv minus v du based on these equations, right? So we have to keep in mind the entire thing that's in the square brackets. All right, so let's write out the full thing now. So our original integral, x squared times the sine of x with respect to x, that's equal to, so this part is good, we have our negative x squared cosine of x, and then I have plus 2 times, and then there's a quantity. So the quantity is going to be uv, so x times the sine of x minus, and then the integral. Now this time we'll have our v du, so it's just our sine of x, and then our du is dx, right? So that's what it looks like after applying integration by parts twice to this original antiderivative. And then let's look at what we have. We now have an integral that's relatively easy. We know how to integrate our sine function. So let's put it all together and see what our final answer is. So we have negative x squared cosine of x plus 2. Now I'll keep the square brackets for now. Let's evaluate this and then at the end distribute the 2. Now this 2 is going to multiply everything in the square brackets, right? So we'll have x times the sine of x. Now the antiderivative of sine is negative cosine. There's already a negative in front of this antiderivative. That makes it a positive cosine of x, and then plus c, right? So now if we distribute the 2, right, so we will have negative x squared cosine of x plus 2x sine of x, so 2x sine of x, and then plus 2 cosine of x. And then we're going to double this constant. But what I'm going to do, instead of writing 2c, I'm just going to write something like c1. That's basically just saying that c1 is twice the constant in the previous line, right? And this will be our antiderivative. Now, you can imagine, for instance, if the problem started with x cubed, then we would likely have to do integration by parts 3 times. If it started with x to the 4th, we would likely have to do integration by parts 4 times to get it to work, right? Well, for certain types of integration by parts problems, there is not really like a shortcut, but it's really just a more efficient way to organize the process, right? You know, basically, we started the problem, we wrote down, these 4 equations, and then we came up with this kind of reduced form, and then we wrote down another pair or another set of 4 equations, and we broke it down even further. Whenever we have repeated integration by parts, such as this, where you have like a polynomial times a trigonometric function, or a polynomial times an exponential function, there's a very efficient way of organizing your work that will lead you to the exact same result, right? So, so when integration by parts must be applied repeatedly. In other words, we have to do the process more than once, like one time just isn't enough. Something called tabular or synthetic integration by parts right? So integration by parts is a more efficient, or you could say effective, let's say efficient. So it's a more efficient approach, right? So again, it's not like you're not cutting corners. What you're doing is you're basically saying, okay, I'm going to do everything I just did, right? But in a more streamlined, a more systematic way. And this is how it works. So let's take this same problem, and I'm going to use this approach to show you what it looks like, right? So we're going to do our x squared times the sine of x dx, but not following like the formal integration by parts process where we write down the u and the du and then the dv and then the v. But this is how it works. We still use Lie to make the choice. So I'm going to set up a table, right? That's why this version of it is called tabular. So I'm going to set up a table, and the table is going to have these headers. One for u, one column is going to represent u, and the other column is going to represent dv. And again, based on our acronym LIATE, we would start with the x squared as u, and then by default, the trig function times the dx would be the dv. Now, when you're setting up the table, we typically don't write the dx, we just write basically the two functions, and we kind of put the differential off to the side. Again, it looks a little less formal, but it's no less accurate, right? So let's write our sine function there. Now, think about it. When we did the integration by parts twice, every time we had a u, we differentiated the u to get du. And every time we had a dv, we integrated the dv, right? So this column is going to be differentiated. This column is going to be integrated. Now, let's say we do it once. So if I did, if I differentiated this once, I would get 2x. If I integrated this once, I would get the negative cosine of x. And you might remember these two functions from the first iteration of parts, right? So for instance, let me just kind of show you, well, actually, let me do it off to this side. So if we were to stop here, and if we did our u times v, that would be multiplying these two, right? And that's what we did. We took the x squared and multiplied the negative cosine x. That's why we got this term right here. And then if we do the u times dv, I would have to multiply across, right? But when we multiplied these two, we realized we still had this factor of x that made the integral just a little bit harder, right? So we did the process again. So let's differentiate this column a second time and integrate this column a second time, right? So if I differentiate this another time, I will get a 2. And then if I integrate this another time, I will get negative sine x, right? Now, the interesting thing about starting with a polynomial, and this goes back to Calc 1, we know if we differentiate a polynomial enough times, eventually that polynomial, it becomes a constant, and if we differentiate it one more time, then this constant becomes a 0. So what we actually do is we make use of that fact in tabular integration. So what we say is if you start with your u as a polynomial, differentiate it as many times as it takes to get to 0, right? So let's do that. So, well, it would take just one more derivative because the derivative of 2 is 0. And then what we do to balance the table, we integrate just as many times. So let's go ahead and integrate one more time. And the antiderivative of the sine of x is cosine of x, right? So what do we do with this information? Well, remember, every time you do a UV, you do a product down to the right. So this would be like the first iteration. This would be the second iteration. And we were able to do the problem after 2. But if we take it a step further, like if we did it a third time, having this 0 really simplifies the rest of the problem. And this is what happens. So each of these blue arrows represent a product. So we're going to multiply this function by this function by this function, which is now a constant, times this function, right? All of these are products, and these all represent u times v. Now, where would the v du come in? Well, that's where you would multiply across, because remember, this would be the v from the last iteration, and then this would be your du. So technically, we're supposed to multiply across here and then integrate that last product, right? So the ones before don't get integrated because those are the u times v. The last product going straight across at the bottom of the table, we multiply these two terms and integrate the result, right? That's the integral of v du. Now, there's just one other thing we need to do to make sure that our formula is correct. Because the integration by parts formula has a negative sign between the uv and the integral of v du, every time you apply it, the signs get flipped. So the way that shows up in the table is that we start with a positive coefficient there, and then we alternate it. Each time we do another row, we switch the coefficient. So a positive x squared, and then a minus 2x, and then a positive 2, and I mean technically a minus 0, right? So in order to apply that minus sign that comes up, again, let me write the formula that I wrote earlier. This negative sign, if for instance we have to apply integration by parts a second or a third time, this negative sign would have to be distributed to the entire remainder of the formula. And that's what happens here. That's why these signs alternate. All right? So let's see if we can put this all together, and just by looking at this table, write down the antiderivative of x squared times sine of x dx, right? And remember, we had the result by using the formal method, and let's make sure that this method works, right? So we're going to take a positive x squared and multiply a negative cosine of x. Well, that's going to give me a negative x squared cosine of x. Next, I'm going to take a negative 2x and multiply a negative sine x. That's going to give me a positive 2x sine x. And then finally, I'm going to have a positive 2 times a positive cosine. So that's going to give me a positive 2 cosine of x. Now at the bottom here, I'm supposed to have the negative of the integral of 0 times cosine of x, or cosine of x times 0. So technically I'm supposed to have this, but when I multiply this last row, having a factor of 0 means that the product is 0. So I have 0 times, and I'm supposed to do my integral. And you can argue that this is where the plus c comes from. This is your constant, right? Yes, I know there might be a minus sign there, but it's still a constant, right? So here's our final answer. So this will be negative x squared cosine of x plus 2x sine of x plus 2 cosine of x. And I'll write it down as minus c, but then I can do the same thing. If I really just like to have a plus, a positive constant there, or adding a constant, then all I have to do is, just like I did earlier, change that minus c to a plus c1. So make it negative x squared cosine of x plus 2x sine of x plus 2 cosine of x plus c1. And in this case, c1 is the negative of c, right? And if I just scroll back up, that's exactly what we got, right? So this is exactly the same as what we have right here, right? But this is such a more organized way. Not only that, but again, if this power of x is, relatively large, then the table method ends up being a lot more efficient than the more formal approach. So I tend to refer to the method that we did earlier as the formal integration by parts, and this is just a more streamlined tabular or synthetic, right? But there's nothing you don't there's nothing here where you're cutting corners. You're doing the exact same operations. It's just organized, I think, in a much more effective manner, right? Let's do another example with this, and let's try something like with the x to the fourth. See what that looks like. And instead of using a trig function, I'm going to use an exponential function, right? And this method works great when you have a polynomial times a sine, or a polynomial times a cosine, or a polynomial times an exponential, right? So here's another example. And let's try something like the integral. And let's say we have 3x to the fourth minus 2x squared, that quantity, times e to the negative 2x dx, right? Again, if we were to do this the formal way, because what I have in parentheses now is a fourth degree polynomial, I would have to do the formal process 4 times, right? 4 times to get it to work, right? Because I'd have to keep reducing the power of this polynomial until it becomes a constant. But the nice thing about the table is you take it a step further. Even when you do get a constant, you don't stop. You go and you take advantage of the fact that the next derivative would be 0. And that makes the rest of the process even easier, right? So, again, based on Lie8, right? So this is our A-type, or algebraic function. And then now we have an E-type exponential, right? So Lie8 says, let's scroll down so we can set up our table, right? We should have enough room here. So Lie8 says the u is going to be the polynomial, the 3x to the fourth minus 2x squared, and then the dv is going to be the exponential, e to the negative 2x. Now, another thing about making this choice, your choice has to be of the form that the u that you choose should be fairly easy to differentiate, and then the dv should be equally easy to integrate. And I think we can see that that's pretty much the case. So let's keep differentiating this polynomial until we get 0, right? So we're going to have 12x cubed minus 4x. Then we're going to have 36x squared minus 4. Then we're going to have 72x, right? Still going. And then we have 72 as our constant, and then the derivative of that constant is 0. So you can see, and basically, whatever the degree of your polynomial, it's going to be the degree plus 1 times of differentiation that will reduce that polynomial to 0, right? So since we started with a 4th degree polynomial, look at how many times we differentiated. 1, 2, 3, 4, 5. So it's always 1 more than the degree. That's the number of derivatives that will reduce a polynomial to 0. But then I have to integrate this that many times. Now, and this is why this particular formula is so useful, right? You don't want to have to do a u sub every time you're integrating this. I mean, look at the pattern. The pattern is you're going to divide by the coefficient of x each time you integrate, right? That's why this formula is so useful. So that when we integrate once, we're going to get negative 1/2 e to the negative 2x. Integrate again, I'm going to have a positive 1/4 e to the negative 2x. Integrate a third time, negative 1/8 e to the negative 2x. A fourth time, positive 1/16 e to the negative 2x. And then finally, the fifth time of integrating, we end up with a negative 1/32 e to the negative 2x, right? So now we have all the pieces that we need. So let's set up those u-v products. And it's always down 1 to the right. So here, 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 there, and there. So those are all the u times v's that we would have. But now we can take advantage of the fact that there is a 0. So when I do the integral of v du, right? In fact, let me write that. Yeah, so we're going to integrate that. And each of these, we're just going to multiply them, right? And then the other piece now, we have to remember to alternate the signs of these coefficients. So this is going to be a positive. This is going to be a negative. Now the negative is going to be of the entire quantity, right? So you might want to even put parentheses around it, right? And then this is going to be the positive. So again, you have this plus minus pattern. And then here, I don't need parentheses anymore because it's no longer a binomial term. It's a monomial. And then plus, and then again, minus, right? So we have all the pieces. Let's write down this expression. Now, this is not going to be a pretty expression, but it's going to be the correct expression. Maybe I could fit it on one line. That would be interesting. So it will be so we have the antiderivative of 3x to the 4th minus 2x squared times e to the negative 2x dx. So it's going to be this positive term times this negative term. So what I will do is these constants in front of the e, I'm just going to put it in front of the entire expression. So I'm going to have negative 1/2 times the quantity 3x to the 4th minus 2x squared times e to the negative 2x. Next up, we have the negative of this quantity times this positive 1/4 e to the negative 2x. Now the negative sign will stay. I'm going to put the 1/4 in front. So it's going to be negative 1/4 of that quantity, 12x cubed minus 4x, again times the e. And keep going. Next up we have this negative 1/8 times that positive quantity. So again, I'll put the negative fraction in front, put the polynomial in parentheses. So that's the 36x squared minus 4 times e to the negative 2x. And then, so we have 72x times 1/16 Now let's see. So I'll just write that. So that's basically 72 over 16 x times e to the negative 2x. Right? So plus 72 over 16 x times e to the negative 2x. And then the last non-zero term is going to be a minus 72. Oh, wait, one thing here. So this one's a negative because of this negative sign there. So that one's a negative. This one's also going to be negative because that's a plus, but we have a negative sign here. And multiplying those two gives me a negative 72 over 32. So negative 72 over 32 e to the negative 2x. And then I have to integrate the product of 0 and this. So it just ends up being the integral of 0, which is going to give me 0 plus c. So that's where my constant comes in. So there's my plus c. And look at that beast, right? So yeah, so that is certainly not simplified. Now, as far as simplifying, there's not much we can do. I mean, we can factor out an e because they all have an exponential in there. And then there will be some like terms because I see an x squared and another x squared, and then there's an x and there is an x, but I'm not going to do that. I mean, that's all algebra. I think the point of this is the fact that we can use this tabular method to really streamline the integration by parts process when it is, it would be a very long process if we were doing it in that formal way, right? So whenever you have repeated integration by parts, when you have functions like where one of your factors is a polynomial and the other factor is either an exponential or a sine or cosine, this method is extremely useful. So definitely consider using it. See you in the next video.